Okay, in this video, what I want to do is to look at the free energy change for the dissolution of ammonium nitrate in water. So this is a typical chemical reaction that's utilized in a calorimetry lab. And the reason that I want to focus on this reaction is because this is an endothermic reaction. If you look at the delta H naught, you see that it's a positive 25,540 joules, or 25.54 kilojoules. So this is an endothermic reaction. And the reason I want to focus on it is because this reaction is an example of an endothermic reaction that is spontaneous. In other words, when we take a certain amount of this salt and we add it to water, the reaction happens without having an outside intervention. So what that tells us is that the free energy change for this reaction has to be a negative number. And this is a different situation than if the reaction was exothermic. So if we just talk about how this would work in a calorimeter for a minute. So, and I want to put a label here. This is called ammonium nitrate. And we're going to take 1 mole of this material and we're going to dissolve it in water. So if I was to actually run a calorimetry experiment, this is what it would look like. We'd have our coffee cup, which represents insulation, and in the cup we would have water, which we would call our surroundings. And then we would add the ammonium nitrate to the water, and then we would observe that it would dissolve. So I'm going to put our reaction in here like this, and this is where we're going to stipulate is what we call our system. All right, and we'll have a thermometer. Now, this is an endothermic reaction. The delta H is 25,540 joules, and what that means is that when we run the reaction in the calorimeter, we would see a temperature decrease. And what that tells us is that energy is being transferred from the surroundings into the system being the chemical reaction itself, which, like I said, is the conversion of solid ammonium nitrate into a solution of ammonium ion and nitrate ion. Endothermic because the surroundings loses energy and our system is gaining it. So relative to the system, this process is endothermic. Endothermic. All right. Now, when we look at the equation that relates the enthalpy of the reaction, or the delta H naught of the reaction, to the entropy of the reaction, you can see that because this is an endothermic reaction, the delta H is actually a positive value. And since when we carried out this reaction, you can actually watch the material dissolve, we know in advance that the sign of the delta G needs to be negative. Yet the enthalpy that is involved in the equation is actually a positive number. So this is going to have the effect of working against the free energy. So what we want to do next is focus on what's going on with the entropy. So the value for this reaction is actually a positive number, 107.3 joules per Kelvin. So the entropy for this reaction indicates that there's actually an increase in disorder. So the driving force of this reaction turns out to be the entropy because it's a positive number. So the disorder has actually increased. And when you look at the equation, you see that delta G naught is equal to delta H naught minus T delta S. Since the delta S is positive, it's this portion of the equation that makes the delta G negative. All right, that overcomes the the positive nature of the delta H to make this value negative. So let's go ahead and actually do the calculation. So delta G naught is going to be equal to, now you need to pay attention when you run a calculation like this to make sure that everything's in the same units. So I'm going to change my delta H into joules. So it's going to be a positive 25,540 joules. That's going to be minus, all right, the temperature at which we're running this reaction is going to be 25 degrees centigrade. So that's 298 Kelvin. And then it will be times the value of the entropy, which is 107.3 joules per Kelvin. Okay, and the delta G, therefore, is going to be a minus 6,435.4 joules. So the first thing to notice is that the sign is negative, which confirms what we already knew going into this. So again, I want to remind you that if you're in a chemistry class that has a robust laboratory program, you probably have already run this reaction in a calorimetry lab. And the reason I want to point that out is because it comes from the point of view of sort of looking at chemistry from a common sense angle. Since you may have already run this reaction, you've witnessed the material dissolving in water, and the fact that it dissolves in water means that the process happens without an outside intervention. And if that's true, then the delta G naught for this process has to be negative, which we see that it is. Now when we look at the number, notice that it's not all that big, so it's actually fairly small in magnitude. So while this is definitely a spontaneous reaction, it has a small magnitude delta G naught, which means that it's actually barely spontaneous, all right, by comparison to other systems, some of which I've talked about in previous videos. Okay, now I want to come back to the calorimetry because there's another angle to this, and that has to do with the relationship between delta G naught and delta S of the universe. So remember that delta S of the universe is equal to the sum of delta S of the surroundings plus our delta S of our system. Now, we already know the delta S of the system, okay, and it's favorable. It indicates that for this chemical reaction that there is an increase in disorder. And that most likely has to do with the fact that we go from a salt to the formation of these two ions, the ammonium ion and the nitrate ion. So we have an increase in disorder for that, which is a good thing. And in fact, it's what's driving this reaction. It's driving this reaction because this product is large enough to offset the issue with the delta H. But I want to take a moment to talk about the delta S of the surroundings, because remember that delta S of the surroundings is equal to the negative of the delta H of the system divided by absolute temperature. So when we come back to the calorimetry, notice that the surroundings actually lost energy. That energy was transferred into our system. So the delta H of our system is actually a positive number, which means that our delta S of the surroundings is actually got a negative number. It's a negative number. And that means that what happened out here in the surroundings, that there was a increase, that means that there was a decrease in disorder. And that's not a good thing. So this was actually negative, and the system is actually positive. So you see, since for a spontaneous process we know that delta S of the universe has to be positive, for any spontaneous process this has to be true. So this is another way to look at what is actually driving this process, because the system had to overcome what was going on with the surroundings in order for the delta S of my universe to come out as a positive number. And again, these two things, the delta G naught and the delta S of the universe, have to correlate. The delta G naught for a spontaneous process has to be negative, and the delta S of the universe for a spontaneous process has to be positive.